How's your game going so far? Well, we haven't really done much yet. We got the point struct implemented, and that's a great start, because now that we can model a position on the map, we can use it to place towers and enemies. Just like we used an object, more specifically a struct, to model the coordinate point, we'll model an enemy next. But this time, we're going to use a different type of object called a class. Let's check out what a class is. Like we created a structure with the struct keyword, we create a class with the class keyword. So right after our code here, we'll say class, and we'll give it the name enemy. Much of the basics that we learned in the last video are the same between structs and classes, so we'll get a good chance to reinforce them here. We'll start off by adding two stored properties to our class. The first one is going to be a variable stored property. So we'll say var life, and we'll set this to be of type int. Stored properties can either be constants or variables, and this determines how those properties behave after an instance has been created. The struct we created had two constant stored properties, which means that after the instance is created, we cannot assign new values to the properties. This is intuitive because we know that constants are immutable and cannot be changed. In programming terminology, when we have a value that we can only get the value from, we can't actually put something in it, like a constant, we say that it's read-only or it's a gettable property. If we can also change the value at any time, we say that it's read-write or a settable property. We set the life property as a variable property rather than a constant because when a tower fires at a particular enemy, we want the enemy's life property to decrease by a certain value. Next, we'll need to figure out where the enemy is on the map, so we'll give it a position property. So we'll say let position. Now, what should the type of position be? Like the built-in types we have available in Swift, like string and int, we can use any custom type we define anywhere. So the type of position here is point. Position is a constant property, which means that after it's set, we're not going to change it. Now, in a properly implemented game, that wouldn't be the case, of course, but we'll make some simplifications here. Now, this means that when we create an instance of enemy, we have to assign an instance of point to the position property. This should give you some hints as to the power of object-oriented programming. We started off by building a custom data type to model a point on our map. Now we're using that data type as a building block for an even more complex one. So much like we use a string, for example, to build up an address, or a number, an integer, to build up another complex data type, we can use our custom data types and build on top of it. Okay, so let's take a look at the first difference between structs and classes. When we used a struct, Swift automatically created a member-wise initializer for us so that we can create new instances. But with classes, we don't get any such automatic or magic behavior. We always need to write the init methods ourselves. Now, we did that in a previous video, so you should be familiar. Let's do it again. We'll add an init method in here. Now again, like before, we start with the init keyword, and then a set of parentheses for any parameters we want to add, followed by a set of braces. We need to set initial values for two properties, the position and life. For the position, we need to create an instance of point, and we can do it one of two ways. We can be direct and require that a point instance be passed into this init method as an argument directly. So we'll give it an argument label, we'll say position, and it has to be of type point. And then inside the init method, we can say self.position to refer to the stored property, should get the initial value position. It can be confusing here. Both of these are labeled position like before, but again, it's standard to give the initializer name, the initializer argument, the same name for consistency. We use self again, then to differentiate between the two. Now, this type of initializer method works, but it puts the burden on creating an instance of point first, and then passing it into the initializer. Now, there are certain advantages to doing it this way, but none that concern us right now. So what we can do is we'll abstract it, and we'll make it easier by simply specifying x and y coordinates as parameters. So we'll say x int and y also type int. Now this is exactly like the initializer for the point struct. So what we're going to do is we need to assign an instance of point now to position, and we can do that inside this method. Earlier, I mentioned that init is a special function. Not only is it a special function in its role and how it works, but we also treat it as special when naming it, and we deviate from our rules. Notice that if this were a typical function or method, I'd name it initWith as the base name and then say x and y as the arguments. Initializer methods, or any method that creates an object, should form a phrase that does not include the first argument. Now this means, simply for our case, that the method name will always be init. Okay, so inside the init method, rather than assigning a position that we pass in as an argument, we'll go ahead and create an instance here. We'll use the struct's initializer methods, and for the arguments, we'll pass through the arguments from the initializer method. So here we'll say x and y. Oops. Now we have an instance of point assigned to position. Okay, so we have an instance of point now assigned to position. And the cool part is that we don't have to decide now what that point will be. Whenever we create an instance of enemy, we can pass in whatever values we need to create that point. We still have an error, and that's because when using an initializer method to create an instance of an object, we need to give all stored properties initial values before we're finished. And right now, the life property does not have an initial value. Rather than doing that in the init method, however, I'm going to assign a value to life directly. We sort of touched on this before, but the difference in doing it this way is that now every instance of the enemy class will have the life property set to 2. So when we create an instance of enemy, using our blueprint, it's going to cycle through and see that, okay, we've specified a value for life and always assign that value. It is a default value for the object. I did this because I do want all instances of enemy to have a fixed initial life. Basically, the guiding factor is this. If the initial value of your object can sensibly be defined before creation of the object, then go ahead and assign that value directly. Otherwise, use an initializer method to delay the assigning of values until you have more data that you can provide. We can't assign x and y coordinates or position values right now, because if we did, what would I choose? Should I put 0, 0 for every enemy? Then all the enemies and all the towers would be on the same spot. Instead, we can decide at the time of creation where we want to place them. Okay, so we're almost done creating an enemy. I'd like to add a single method to our class named decreaseLife. When an enemy is fired upon by a tower, the decreaseLife method is called and the enemy's life goes down. The rate at which the life of the enemy decreases is determined by a factor. So first, let's write our method. We'll say func decreaseLife. And we're going to give this method a parameter that accepts an argument for the factor by which we're going to decrease our life. We'll give this method a local name or argument a local name of factor of type int. But I want this to read much more Swift-like, so I'll say by for the external name. So now it'll read at the call site when we actually call the method, decrease life by, and then some value. Now, since we're not returning anything from this method, there is no return type. Inside the body, we'll simply decrement the life by the amount of the factor by using a unary minus operator. So we'll say life equal or minus equal factor. Remember, this is the same as saying life equal life minus factor. So if the value we pass in here, if the factor is 1, then every time we call decreased life, the life decreases by 1. Now that we have the enemy, let's go ahead and figure out what the tower looks like.